Today is March 13th, 2012, and this is AP Statistics at Berkeley High School. This is the finishing up of the 12-1 lecture having to do with inference and regression. We finished up yesterday with the idea that this new set of regression procedures that we're going to use with, this new set of inference procedures that we're going to use with regression have more conditions than we have had in previous regression procedures. Besides the standard unbiased and independent conditions, we have a linear condition. Well, again, we're doing inference having to do with a linear relationship. We've got to look to see, by looking at the scatter plot and looking at the residual plot, whether the relationship is really linear. The next new condition is that we have equal variances. We look at that and we say, when we look at the relationship of the data to the line of best fit, does it spread out equally along that line? Again, the best way to look at that is looking at the scatter plot, but then also looking at the residual plot, where we should see the residuals spread equally throughout the entire data. And then lastly, we have this last condition of normal. Now, this isn't normal in the sense that we have a single data set that shows no abnormalities. But instead, we have two data sets here. We have an X list and a Y list. We have our explanatory variables and we have our response variables. And what we want is, in each of those data sets, the data to be normally distributed through the X values and Y values. Why this is important is because the foundation on which we're building the inference with regression procedures is the idea that for any particular X value, there is, of course, a Y hat value that's found on the line of best fit. Now, we don't expect that the X value will always perfectly predict Y, but instead there's a variation having to do with the Y values coming from any X values. And those Y values get normally distributed across those different values. That although there's variation, the center of all those Y's would end up being on the line of best fit. Okay? And we'd like those normal distributions that are centered at any particular Y hat value to be having the same variance, having the same standard deviation. Okay, so for each possible value of the explanatory variable Y, the mean of the, or explanatory variable X, the mean of the Y values ends up being on the line of best fit. Okay, and again, the normal distribution shows how those Y values may vary. Now, this is nice because we end up getting an additional bit of bang for our buck here. Not only that, given some X value, can I predict a Y value, but I can actually create a confidence interval around that predicted Y value, saying I believe that that the Y's that you're likely to get out of those X's have this much variation that will be found in this particular interval. If you can imagine, for any particular one of these normal distributions, the middle 95% creates a confidence interval that's centered around that Y hat. I can predict the Y, but then I can also predict with a particular level of confidence that's going to fall in a particular interval. Okay. And it's the value of sigma that determines how closely or how far away those Y values fall. Okay. If sigma is small, then we predict the Y's with a lot of accuracy. If the sigma is large, obviously we have a much larger confidence interval on which the Y values would fall. Okay, so let's go through checking each of these conditions. So if we're going to check the linear example, if we're going to check the linear condition, how are we going to do that? Well, run the scatter plot on your calculator, or look at the scatter plot that's giving you. Look for a linear pattern. Okay. Also, given that data on the scatter plot, run the regression so that you get a residual list, and look at the residual plot. Does the residual plot show a pattern? If it does, we say that's evidence against the claim that's linear. What we should be looking at in this residual plot is noise, randomness. There's chance variation that happens through sampling process. Okay? How about on the independence condition? How are we going to check for that? Well, as with before, we need to have independence of sampling. So large population sizes with respect to the sample is required. Also, random assignment helps to ensure that the data is independent, has independent observations. Okay, how do we check the normality of the x values and the y values? Well, we already have, if we're doing it on the calculator, we already have all of our x's in probably in list 1, all of our y's in list 2, and there's a particular plot that checks normality. It's called the normal probability plot. It's the sixth option in your stats plots menu. If we see those normal probability plots with a nice straight line, then we say that the distribution of data is linear. If the normal probability plot is linear, that means the data is normal. If the normal probability plot shows any sort of curviness in it, that means it's probably skewed. Okay. Again, if we're going to check the equal variance condition, we look at the residual plots, and we're looking for, on that residual plot, an equal spread both up and above and below that line equal of variance equals 0, residual equals 0, and we should see that equally scattered and spread out across the entire data set. And then, of course, how do we check the random condition? We require that the data was collected using simple random sampling or some sort of random sampling. If it's an experiment, then we want random assignment into the groups. And I guess is this an acronym or is this a mnemonic? I can't remember which one's which. To help you remember the 5 conditions. I guess if you pronounce it liner, then it's a mnemonic. No, it's an acronym. Okay, so NASA is an acronym, but FBI acronym. Wait, which one isn't it?
Please excuse my dear Aunt Sally, mnemonic, acronym, FBI or NASA.
Okay. All right. Remember that, don't you? From algebra? It's the order of operations, parentheses, exponents, multiplication, division, addition, subtraction. Not to be confused with, I brought Clara home for overnight.
What's that?
Those are the diatomic molecules. All right. Oh, sorry. Or proud Vikings never rape turtles. That's the ideal gas law. Continuing on. We have an experiment. Okay, so Mrs. Barrett's class did a variation of the helicopter experiment. Now, we didn't do the helicopter experiment, but here's the general idea was that they took paper helicopters, they dropped them from a particular height, and then they saw how long it took the helicopters to fall down. Right? So they have different drop heights. then they have different times it took to for those helicopters to fall. And in this drawing, or in that plot, there's the scatter plot of their data. And from that, we can ask the question, is it linear? There seems to be a general linear pattern. It's kind of weird because we have this kind of bunching, because they only dropped it at 150 centimeters, they only dropped it at 200 centimeters, so it's kind of bunched up. But do we see a general linear pattern in the data? Okay, I'd say we do. All right, next thing they do, okay, so that handles the linear condition. I was what, independent? Right? What about equal variances? Well, the equal variance question says, okay, if you look at the residual plot of the data, do we see that the data for any given x is about equally spread? Well, I don't know about you, but those spreads look a little bit different there. I might say we have a proceed with caution on the equal variances, condition. Okay. What about the normal condition? Let's go right to the. They looked at it twice for normal. They looked at it as a histogram, but this is the one that I really want you to focus in on. That's the normal probability plot. And again, the idea is if you take the data and put it through a normal probability plot, if the plot is linear, the data that it came from must be normal. Would you say that that normal probability plot looks pretty linear? So we probably then will pass the normality condition. Okay, let's see if we missed anything. It says linear. The scatter plot shows a clear linear form. The residual plots so that the residuals are centered at 0. Looks good. Normal. The histogram of the residuals shows a single peaked unimodal, meaning a single humped, bell shape. It looks to be normal. There you go. All right. Equal variance. Looking at the residual plot, you can see the clumps of residuals. And what do they say about it? Flight times seem to vary more for helicopters that were dropped at a height of 307. They're saying by their view of the residual plot, it looks like they do not have equal variances. Proceed with caution. And then independence. They said that the helicopters were released in random order. They were randomly assigned to which height they were dropping from. So they have the independence. Not to mention, we could say that the population of all of helicopter drops is probably at least 10 times their sample. They could have done it 10 times more. There could have been 10 times as many things in the population. Okay, and there's that random again. All right. So, except for the slight concern about the equal variance, looks like we meet the condition. The conditions of the inference testing. So let's go on and say, all right, if we met the conditions, what does the inference test look like? I want to make you recall that all inference testing has to do with the same thing, and that is taking a sample, finding statistics, using those statistics to estimate parameters. In other words, using sample data and using it to find out something at the population level, estimating the parameters. Remember, we talked about yesterday that when we've been doing linear regression on our calculator, they assign the letters A and B to the slope and to the vertical intercept. I should have said it the other way. A and B to the vertical intercept and the slope. But the calculator believes those numbers to be samples, not an entire population worth of data. We say that A, the statistic, is the estimator of alpha the parameter. The true vertical intercept, as if we did a linear regression on all the data in a population. We say that B, the slope, the sample slope, is an estimator to beta, the population slope, or the true slope. The true slope we would get is as if we did a regression with all the data from a population. So alpha and beta are unknown parameters. If we calculate the slope B, it is an unbiased estimator of the population slope beta. A is an unbiased estimator of the population vertical intercept A. The remaining parameter that's unknown is sigma, which describes the variability around the line. Remember how we said for any particular y hat, we actually get a range of y values that we think the y's would fall into? That sigma is unknown to us as we look at this sample data. So the least squares regression line that's using these sample data unless we have absolutely perfect data, there's variation of the data around that least squares regression line. Now, what we'd like to know is sigma, how much that data varies around that least squares regression line. But we don't know sigma because it's a population number. So we're going to make a best guess. Our best guess, we're going to call S. S for standard deviation, but S because it's a sample that we're getting it from. And we're going to find that by taking the sum of the residual squared and then dividing it by n minus 2. Now, you might ask the question, why n minus 2? Well, we're about to enter into another place where we have degrees of freedom. And in this particular instance, we have n minus 2 degrees of freedom. I've talked before about degrees of freedom as being how much information do you need to have before you know everything. In the case of chi-square, we said degrees of freedom was 1 minus the categories. Because if I told you that the M&M that I'm looking at is not yellow and not orange and not red and not brown and not blue, your conclusion is that M&M must be green. In other words, when I give you 5 pieces of information, it's like giving you the 6th for free. In this situation, if we had a data set and we were calculating a least squares regression line, the moment I gave you all but the last 2 pieces of data, the last x value and the last y value, if I told you the least squares regression line, and I told you all but the last data point, the moment I tell you that, you actually would have the ability to calculate what the last data point is. So we say that in the case of linear regression inference, that there are n minus 2 degrees of freedom. Okay, and our S value, our best estimate to sigma, the amount of variation around that line of best fit, is going to be the square root of those residual squares divided by n minus 2. I think your calculator will give that to us so that we don't have to calculate that by hand. All right. Now, moving away from the calculator for just a little bit, we've got to look at some output from a computer program called Minitab. And one of the reasons why we have to do this is that our calculator actually does a pretty poor job of doing inference having to do with linear regression. So we're going to work more with the Minitab output in this chapter than we do with the calculator. Here's the Minitab output. We've looked at this before. Let me go through hit the highlights. So this is the regression analysis of flight time in seconds versus drop height in centimeters. Okay. The thing that listed here, that's our y. That's our response variable. The thing that's listed here, that's our x. That's our explanatory variable. In this case, we believe that by varying the drop height, we are forcing the amount of time that the helicopter falls to vary. Right? On your calculator, they just call them X and Y. Item number 2. When we do it on the calculator, we get a linear regression equation. We say we get a predicted Y value, a Y hat, that's associated with some X value, explanatory variable. And on the calculator, it simply says A equals and B equals. In the Minitab output, on the other hand, they kind of hide where those numbers are and don't make it nearly as clear. We see that we have this thing called drop height, and we see we have this column called coefficient. The intersection of column and coefficient is the coefficient on drop height. But drop height was X. The coefficient on X, the number that we multiply on X. Oh, the coefficient on drop height is just a fancy way of saying the slope. So from this output, you should be able to look and say, oh, I can see that the slope is this really long number, 0.0052, blah, blah, blah. From this output, you also should be able to tell me what A is. Again, it's sort of hidden in a strange way. It is a coefficient, but it's a coefficient on the constant. Well, it is the constant. And in our linear regression equation, A is just a constant there. So we'll have to be able to look at this output and say, oh, in order to find the y-intercept, it is the coefficient on constant. Now the other thing that comes out of your calculator that you're really, really used to is also getting an R and an R squared value, because you've been looking at those to find out the strength of the linear relationship. They don't give you the R value in this output. So they do give you the R squared value. The R squared value is listed here, 0.912. Now, is there only way to, from the R squared value to find the R value? Jason, your moment has arrived. How can I find, from the R squared value, find the R value? Thank you. You did not disappoint me. So if I take the square root of this, I will get the R value. Now there's only one other thing that comes with the R value. Remember, the R values can either be positive or negative. How are we going to know whether this one's positive or negative if we start with a value that has to be positive, the R squared value? And the answer is we steal whatever the sign is on the slope. If the slope is positive, then the R value is positive. So from this output, we've got essentially all the information that your calculator would also give us. And again, I'm telling you right now, I need you to be able to pull that information out just as easily as if it came off your calculator. Everyone okay with all of that? Because there's more. We talked about the fact that we would like to know how much variation is there about the vertical lines that go through the line of best fit. The S value, the estimator of sigma. Well, the estimator of sigma is right there in our Minitab output. So what does that mean? Well, a couple of things. One, if we were given a particular drop height and we're asked to predict how long do you think the helicopter is going to take to fall? Well, you take that drop height, you plop it into X, we get a value out which will be the center of the distribution of y values that come out of there. How would we then go and say, well, what are the range of values that we think that y is likely to have? The range of values and the range in the times between the quickest helicopter and the slowest helicopter. Well, this S is a reasonable estimator of how much variation there is. If flight time is in seconds, that value S says that the average difference from the predicted point is about 0.168. If it's normally distributed, we'd say that about 95% of all helicopters fall within 2 times that amount. About. Because 95% of all things in a normal distribution are within 2 standard deviations of the mean. So we could say for any predicted y value, if you add 0.32 to either side, you're likely to capture most of the helicopter drop times. All right. Let me see what else they want me to bring your attention to. I'm going to wipe out my drawing and see what they have to say. Make sure I hit all the high points. Did we get this idea down?
Yeah.
Flight time hat. Why hat again? Because it's not a real flight time. It's a predicted flight time. Okay. And again, you see the y-intercept. They see the slope. So we got we got that idea down. What's next? And we say that value that came out of the mini-tab is a B value. It is a statistic. It is an estimator to the true beta. The beta that would come if we dropped all the helicopters and measured all their flights. It also has, something I did miss. It also has an interpretation. The interpretation says, for each additional change in the x value by 1 unit, we have this change in the y value. Or in this case, for every additional centimeter that I lift up the helicopter, which isn't very much, I expect a 0.005 increase in seconds in the amount of time it takes for the helicopter to fall. Slopes have interpretations. For every change in 1 unit in the x direction, this is the amount of change in the y direction. All right. And why did it move? Okay. The A is the y-intercept. We talked about that. The A values, by the way, tend not to be very useful. Because we tend not to have things where our x values are around 0. But it is it helps us to draw the line of best fit. Okay, and there they are pointing out S, the estimate for the standard deviation, the average size of the error for any particular y is about 0.168. Okay, the sampling distribution of B. Yesterday I started hinting at this idea that if you take sample after sample from this data that has both x and y values, sample after sample, you can run linear regression. You get B after B after B. Those B's won't always be the same because sampling variation causes them to change over time. This is in fact actually the sampling distribution from many samples of size 20 taken from those 202 eruptions of Old Faithful. Here's what we'd like to say. This distribution of B has qualities that we should exploit. Item number one is that the center of the distribution of B's is actually going to be the true slope beta. Item number two, that this distribution looks normal. Item number three, is that it's got a standard deviation that's somewhat predictable. Shape normal. Center 10.36, which is about the same as the center of all the 222, the slope for the 222 data points. And then it's got a spread. Now, here's where it's going to get a little bit more confusing. We already talked about a spread. We talked about a spread that goes out from any particular y-hat. And this spread we called sigma. But this is another spread. This is the spread of how much variation do we have in the slope data. And so you could probably hardly see this, but that spread we have a different symbol. We call it sigma sub b, the spread of the b values, the spread of the slopes. We need to make sure that we don't confuse those two. Now, back to reality. We don't ever know what sigma is. Sorry, sigma of b is. We'd only know that if we had population level data, and we hardly ever know what's going on at the population level. So, we got a problem. Our problem is not a problem that we've not seen before, though. In other situations where we've had formulas that are dependent upon sigma, I don't know, z is equal to x bar minus mu over sigma divided by root n. We've had this problem before. We've had a formula that references a sigma that we don't know. And so, I would like you to recall from memory's vaults what we did when we had that situation before. We threw our hands up, we said we can't do it, and we went home. Took a nap. We didn't use sigma, we used standard error. Very good. What did that look like from the formula standpoint, Paul? S of x divided by root n. You agree? Remember that? When we don't know sigma, we went to this other version and say that again, Katya? Thank you. And when we did that, we no longer had a z, we had a t. Well, guess what's going to happen again? We have a problem. We don't know what sigma of b is because we don't know population stuff. So what are we going to do? We're going to use an estimator for sigma of b. And we're going to call it the standard error of b. Just like Paul had said. And the moment we move away from the standard error of b, or from sigma to standard error, guess what we have now? We no longer have a z distribution, even though it looks normal. We're going to have to force to use that more conservative, harder to find significant test statistic called t. Let's see how that plays out in the lecture. All right, I'm going to wipe this out. And we'll move forward. All right, and there it is. In practice, we don't know what sigma, the population, for the population regression line. So we estimate it using the residuals S. And we estimate the spread of the sampling distribution with the formula, the standard error of B, just like Paul said, is equal to S, and S was that number that we just calculated a little bit ago. It was the sum of the residual squared divided by, what was it, the square root of n minus 2. That S value, so we take that S value and we divide it by the standard deviation of our X values, and then we also divide it by the square root of n minus 1. And that formula, I believe, is on your formula sheet. Can we check that, Melissa? Make sure it's on your formula sheet. Oh, that's your cheat sheet. Who's got the formula sheet handy? I think this is on your formula sheet. I think both of them are on the formula sheet. Although, as you probably have noticed a great deal of the time, how often have you been referring to the formula sheet? Not much, right? So it's going to be there, but it may be not as useful. Actually, it is on the bottom of page 3, and it's listed as S sub B1, and it's got the entire formula where this S is actually written out in that form of the square root of the residual squared divided by, and it's a whole big mess. It's on the formula sheet. Let's move on. So, what we end up getting, if we follow this idea through, from earlier times, that a test statistic, like a z-value, is equal to an estimator in the form of a statistic minus a parameter in the form of a mu or a p or a, in this case, beta, divided by the standard deviation of the parameter, standard dev of the parameter. We've had that basic outline for a test statistic. Well, we have that z is equal to b minus beta over sigma of beta, or sigma of b. Actually, standard deviation of a statistic, that parameter there. We'll correct that. Okay, step one more forward, like Katya and Paul had said, but we can't do that. Why? Because we don't know that, so we're stuck with t is equal to b minus beta over, we'll call it the standard error of b. And that will be our test statistic. That will inform us about some beta or some b value and how it conforms to some beta. Wait, we got rid of sigma because we didn't know sigma. How do we know beta? And the answer is we don't know beta. But we can make a test to find out whether the b we got was dramatically different from the beta that we expected. In the same way that I did a data collection and I got an x bar, and I can compare it to some mu. Not some mu that we know, but some mu that we suspect. Same idea. All right, let's go get rid of my writing and let's see what they have to say on the subject. So there it is, our test statistic, which is going to show up in step 3 of our 4-step process, is t is equal to b minus beta over the standard error of beta. And since we're using a t distribution, and t distribution isn't one distribution, it's actually many families of distribution. Sorry, a family of distributions, we have to know that we're going to be using t minus n minus 2 degrees of freedom. Okay. So we've got all the elements to actually start doing inference testing. We have all the elements to start saying, hey, I did some sampling and I got a B value. Does that B value support or refute a claim about some population beta value?
Another one of those formula sheets.
I think I put it in your hanging folder, but you checked out, I think. When you were asking yesterday, I think everyone was asking, I put it in there. Can I ask a favor? Is it hot in here? Would you open the windows? Like, I don't know if it's just because I'm walking around and you're, but it's, I'm starting to get warm. And Megan's, yeah, there you go. Oh. Did you get hit in the face, Hannah?
Yeah.
I'm sure Megan didn't mean it. Pretty sure. She hasn't apologized yet, so we can't tell. Did you apologize?
No.
Oh, okay. You're not sorry?
I'm sorry.
Okay. That was less than a resounding. Okay. So let's go ahead. Let's go ahead and then put the final pieces together. We know that with inference testing, what do? There's essentially two things that we do for inference testing. Either we reject or fail to reject some H0 claim having to do with a statistic, having to do with a parameter, or we do something like a confidence interval where we say we believe that the real population level value falls in a particular range. So if we take this jumping off point, we have done the confidence interval how many times? I don't know, 4 or 5 times? Same idea. It's a statistic, an estimate, plus or minus. And we call this stuff combined the margin of error. We find the margin of error by taking some critical value from one of our probability tables and multiplying it by the standard deviation of the statistic. Let's see what we're going to do for this one. If I want to try to guess what the true value of beta, I think I misspoke that. Let me say that again. If I want to get an estimate of beta, the true slope of the regression relationship, I'm going to take my best guess at what beta is. And it is, I'll try that again. And it is a statistic. But what statistic in this particular case? I'm trying to estimate beta. What statistic is an estimator of beta? It's a slope. What letter do we use for slope? B. What's the difference between B and beta again? B is for sample. Beta is for population. I want to figure out what's going on at the population level. Why don't I interview everyone in the population then? Too expensive. So I have to cut down my dreams to something that's manageable. So I'll interview everyone in a sample from the population, and when I do that and I do a regression line, I get a B. And that B is the statistic, it's the estimator of the thing I really want to find out about. I really want to find out beta. Plus or minus, a critical value. We've had 2 critical values in this class so far. Their names were Z star and T star. What are we going to use in this case? T star, because we talked about the fact we don't know what the population standard deviation is. Critical value, T star. And then the last thing, the standard deviation of the statistic. How much variation is there in the slope? And that's this new value that Paul conjectured its existence, the standard error of B. And when we do that, what do we get? A range of values that we think that beta exists in. How confident are we going to be that the beta actually falls in that range? Answer, depends on what critical value we use, because the critical values are based on confidence level. On what conditions can we use this formula? Unbiased, independent, linear, equal variances, normal. The same conditions that we talked about earlier. Yeah, let's see what the publisher has to say to make sure I have hit all the salient points. Okay, so did we get that right? Yep, the statistic is B plus or minus T star SE of B, standard error of the slope. And we get a T interval, a confidence interval for the slope. The standard error, by the way, I don't think on any quiz nor on any test am I actually ever going to ask you to calculate the standard error. Which is good for you, right? All right. So we better be able to find out where it is when we need it. Right? And T star is the critical value for a T distribution. How are we doing on time? 18 minutes left? 11 minutes left? 18? Okay. All right. Back to this mini-tab output. Where's B? Coefficient on drop height. There's B. So if I ask you, please give me a confidence interval, you better be able to look at this table and say, oh, B, the thing that starts off the whole process, is the coefficient on the explanatory variable, plus or minus T star. Where are we going to find T star? 70 minus 2 is degree of freedom, but where are we going to find the T star value? Your probability tables, because that's probability tables. I think I would like to be 95% confident on a confidence interval for the value of beta. So, on that T star, on that T table, I've got a combination of 95% confidence, and Paul said that there are 70 helicopters, so how many degrees of freedom? 68 degrees of freedom. Now my guess is there's not a line that says 68 degrees of freedom. So should we go up to 80 or down to 60? Down to 60 because it's the more conservative thing to do. So please tell me, what is the T star value associated with 95% confidence and 60 degrees of freedom? 2.00? Really? Exactly?
Yeah.
Wow. Okay. Multiplied by, according to our formula, the next thing is the standard error of B. The standard error of B. The standard error of coefficient. The standard error of B is listed on the mini-tab chart. Now there's a lot of other numbers there that I don't want you to worry about right now. Okay? But there it is. There's your standard error of B, and that's what we plop right there. Oops. And doing what we tend to do with those problems, we're going to take this value, subtract it by 2 times that. Abby, you're going to come to my rescue?
Where's that boy?
I want you, well, I tend to do the subtraction first because I like to write the lower end of the confidence interval first. So 0.0057244 minus 2 times this 0.0052. Okay, and then do second enter, and then just change the plus sign, the minus sign to a plus sign.
0.0110452. Or, sorry, 0.0110452.
Really? Okay.
We need to make a boo-boo.
No, I think she's fine. I think she's fine. No, that can't be it.
Yeah, it's not like that either.
Because we're adding only 4 thousandths to this. I think I would guess it'd be something like 0.0061. Is that closer to what the other people are getting?
Yeah, I'll see what I did. It's 2.0, right?
2.00 times 0.0002.
I got 6128.
6128. Okay. Something like that. As with other things, I'm actually less concerned about your ability to put numbers in the calculator right as compared to the concern that we understand the underlying concepts behind these calculations. All right, so from the Minitab output, we actually have everything we need to be able to calculate a confidence interval. What does this confidence interval mean? With 95% confidence, we believe that the true slope, the slope as if we dropped every single helicopter and we had population level information, the true slope of the relationship of height to drop time is between those two numbers. Okay, let's see what they say. I hope so. So there they are, grabbing the standard error of B out of the table just like we did. And there's their calculations. We can do this, right? All right. You got what? 5 minutes left? Okay. And the mantra remains the same. With 95% confidence, we believe that the true, and then we have to describe the parameter that we're investigating, the true slope for drop time versus for drop height is in that range. All right. Okay, so here's another example. In this example, we have what we have is that we're not going to be able to get through this. Okay, here's what we're going to do. We are delayed one more day. We are going to take the quiz on Thursday now. All right, what I want to do is I want to spend one more day, and what I'd like to do is I'd actually like to do this example, not just me going through it. I actually want to do this first thing tomorrow, and I actually want to start with you doing this on your calculator. So do me a favor. For tonight, you don't have homework, but I do want you to do this for me. When you come in tomorrow morning, if you have your own calculator, I would like for you to put the NEA change numbers into L1 and the fat gain numbers into L2. All right? This example is in your book. So you have the ability to get this in your calculator ahead of time. I'll save us a little bit of time tomorrow. All right. So I'll close off the recording.